Okay, so welcome back to the lecture series, and today we start off from the same point where we left the last time. So last time we did that excellent backward search and made heuristic functions. What was the problem? The complexity is still exponential. The goal will generate b children, each one of them b children. At level 2 I have b square, level 3 I have b cube. Eventually I get some node which is true at the source and I stop excellent. And response to that was there will be excellent heuristic. Did we get excellent heuristic? No. We did construct some rudimentary heuristics, and as experience would now tell you that the heuristic estimates by the so-called relaxation are way too simpler than what the real world costs are. That increases your heuristic error and your search goes absolutely slow. So today what we're gonna do is we're gonna pray that can I solve this exponential problem and make something which grows linearly like a linked list and not exponentially like a tree? Answer is of course no. Why would I have waited for so long to tell you this amazing technology? So we reduce our problem and we say a simpler thing, that now I'll not try to solve the complete problem. I will just try to make a heuristic function, and I restate my problem that instead of solving the problem in an exponential manner, could we make some assumptions and convert that tree into a linked list so that my search goes linearly with time, it doesn't go exponentially with time. And of course that won't solve the problem. I will make in some assumptions on the way that I'll not get my solution, but it should be an excellent heuristic function. And because it is an excellent heuristic function, I will be able to accelerate my actual search algorithm. And how do I convert a tree into a linked list? So let's go in the classic state. So there was something A that was generating B, C, D, that was generating E, F, G. So that's exponential H, I, J, K. So I say, how do I convert it into something which is linear? And believe me, what I'll do is I'll say it's A and then any one of B or a C or a D and then any one of a E, F, G, H, I, J, K. And what I'll do is at every state I'll keep clubbing in whatever I get. I'll keep clubbing it whatever I get and I'll go in as a linked list. That is what's gonna be at top level my mantra for trying to curb the complexity. So let's get started with it. The topic will be called as the planning graph. And the previous example was just as any general state. Now we'll talk about the specific states that we have. And let's take in a very simple problem for that specific states. The problem has a special name. It's called as have your cake and eat it too. So let's very quickly write down what is the definition of this problem. My initial state is that I have a cake. Why did I choose a new problem? I want something with very simple planning graph. So this problem has the least number of states possible. My goal will of course be that I need to have my cake and I should have eaten it too. Now I'll come on to the actions. My actions are: number one, the action is called as eat cake. And what happens when you have to eat a cake? The precondition is that, of course, in order to eat a cake, you need to have a cake at the first place. And the effect of it is that, oh my God, what happens when you eat a cake? You no longer have a cake. And why don't you have a cake? Because you have eaten it. So how do I have my cake and I would have eaten it too? I take a second action which is called as a bake cake. So the precondition of the bake cake is the fact that you do not have a cake. And now remember, I mean, ideally you could bake in any number of cake, but we have a state space where it's either true or it's false. And the effect is that if I have a baken a cake, then of course I have a cake. And let's very quickly go into solving this problem using only the initial state. So my initial state is that I have a cake and I haven't eaten a cake. Now I'll have another change of conventions over here to make the visual appeal of the planning graph better. So traditionally what we are used to, I draw states like this as vertices, I draw arrows, and then I draw another state. I write down the name of the action above it. So the circles become the states and the non-circles become the actions. Now I'm gonna revert it up. So what used to be enclosed in this prison will now be free. It won't be enclosed in this prison anymore, and what used to be free will now be enclosed within this prison. It's exactly the same thing. It says S2 is obtained by applying action A on S1. It's exactly the same thing. It's just that if you look at the second one, you'll find it a lot more neater. So I shouldn't be talking about neatness with my handwriting, but that's what we have. So this is the source state. It's also called as state at level 0. Now remember, I won't expand a tree. I'll expand something like a linked list, which will go on and on and on. So linked list which just has the source, which has one node, which has two nodes, it's called as levels. So this is source, which is level 0. Using that, by applying action, I will go to level 1, level 2, level 3. So I've got two actions. Let's see which of them can I apply. And remember, this time I won't apply different actions and generate different children. I'll apply all the actions and I'll take a union of all the children to see what does it produce. So here we go. So my first action is, what is a eat cake? It's a very good action. So eat cake has a precondition half cake. Half cake is true. Luckily, half cake is true, so I can apply this action. And remember, by that action will be inside the cage. So eat cake is applicable. It will be caged. And I'll draw arrows from the preconditions over here. So the precondition of eat cake is a have cake. So there's an arrow which leads from the have cake to the eat cake, and the effect is not have cake and eaten cake. So very funny, the effect is I not have cake and I have eaten a cake. So it produces two ground literals. Now remember, there are no variables over here. There's no xy over here. They are all ground. So because it has two literals generated, two propositional constants generated, which are right here, I put an arrow from this action to what all does it generate. So let's apply the second action as well. So the second action was called as a bake cake. The precondition is not have cake. Action is not applicable. Good for us. The action is not applicable, and because the action is not applicable, I can only apply one action. So it gives me the states at level 1. Simple enough, and I could go level by level. But one thing that you see is, initially I also had something called as have cake. Now it's gone. It's no longer there. What if I don't wish to apply any action? Or as we looked at previously in classic searches, what if I wish to apply the classic no operation? I don't feel like doing anything at this step. I should be allowed for it. So we've got special no operation actions, one for every literal. It's called as a persistence action. Oops. So the no operation actions have a specific name, and the no operation actions have a name called as the persistence actions. They are equivalent to no operation, do nothing. So the precondition is the same as effect, is the same as its name. So let's write down the persistence action. So the persistence action have cake does nothing. So the precondition is have cake, and the effect, guess what? I do nothing, have cake. So if I had a cake, I did nothing, I have a cake. Simple. Do nothing. So let's apply persistence action now. Because it's so simple, precondition is equal to effect is equal to name, we will not write down the name, or instead of a name, we will just say it's so obvious that I don't write down. Ideally, I should have written the name like this, which has a precondition have cake, and it has the effect have cake. But because it's so simple, I just write it down like this. Have cake and have cake. So let's apply the persistence action over here, of course. So 2 literals will make 2 persistence action. 10 literals will make 10 persistence action. I don't feel like writing the name, so I'll just put a box over here, empty because it's obvious it's persistence. So have cake and persistence action, not eaten cake. Simple enough. Now, even before I go, there are so many things which are fundamentally wrong about this. Could you just generate literals and literally take a union of all of them. So like in the forward search, I apply all actions that generate complicated states, each one with a linked list of, or each one with an array of many propositional variables, and all we do is we just take a union of all propositional variables. So if half cake was in 23 out of 50 children, it gets common, it gets only one entry. Could we take these kinds of union? Obviously no. And that's my assumption. So I will not generate different children with different propositional set of variables. I will instead apply all actions, and whatever children they generate, I'll take in a union of all of them. The other thing, of course, it's obviously wrong. How can you have in one state have cake and not have cake? Assumption. So as of now, let's continue and let's just do it at one more level. But then I've got an interesting layer in my linked list, the arrow layer. So let's call it as the action level 0. Writing down the names, this is state level 0, state level 1, and this is action level 0. So let's do it. Let's apply action level 1. That will give me state level 2 very quickly. What are our actions? So firstly, they are persistence action. Needless to say. So that's have cake. That's not have cake. That's eaten cake. And that is not eaten cake. And I've got two actions, eaten cake with a precondition have cake. Do I have a have cake here? Yes, definitely. So let's write it down. I have cake, eat cake. And the effect are same, not have cake. Right over here. And of course, it's because I have eaten the cake. So I've eaten the cake. These two are the effects. The second one is, what is a baked cake? Do I have not have cake? Yes, I do have a not have cake. And because I do have a not have cake, so let's say that I add a bake cake. Oops, so little bigger. So bake cake. And the effect is that I do have a cake after that. So the effect is that I do have a cake after that. So it's not the beautiful drawing that you have, but we're going level by level. And let me write it down over here. So of course that's A1 and that is S2. In English language saying that it's action level 1 and this is state level 2. Now let's see what have we done. So all that I say is that my backward search, my forward search, they generated b square, and they would have gone all of it. I've got one utility now, and that one utility is that if I have got n ground propositional variables, each one of them can take in either true or false. I've got a maximum of 2n propositional variables, n entries here as true and n entries here as false, maximum 2n. So my any level will have a linear number of propositional variables, and using that I'll go level by level in a linear fashion. So no exponential complexity.